On this slide, I'm going to explain about reversible reactions and dynamic equilibrium. A reversible reaction is a reaction that can occur in both directions, the forward and the backward reaction. As shown in the equation A plus B reversible to C, the double arrow means that the reactant can form into products, and at the same time, the products can break down to reform the reactants. At the start of the reaction, the concentration of reactants A and B is very high. This is because the forward reaction happens very quickly and producing more product C. As the reaction continues, the concentration of reactants decrease, while the concentration of product is increased. This is because the forward reaction to slow down, while the backward reaction becomes faster. After some time, the rate of the forward reaction becomes equal to the rate of the backward reaction. At this point, the concentration of reactants and products remain constant, even though both reactions are still happening. This condition is known as the dynamic equilibrium. The reaction does not stop, but it is balanced. In this part, I will explain how to calculate Kc, Kp and Qc, which are used to describe the chemical equilibrium. For the Kp, is calculated by using the partial pressures of gases. First, we need to write the Kp expression using the partial pressures. Second, substitute the given pressure values, and we can calculate the final value. Qc is calculated the same way as Kc, but it is using the initial concentration. For the steps, we need to write the Qc expression. Second, we can substitute the initial concentration, and we can calculate the value of Kc. Finally, we can compare the Qc with Kc to determine the direction of the reaction. So, the reaction shift is to the left.
Okay, so next I'm going to talk about derive and use the equation. Okay, first we have to know K is a unitless number because there is an equal number of moles of product gases as mole of reactant gases in the balance equation. Therefore, we can use units of molecule per liter instead of moles per liter to determine K. The expressions for K is the product concentration divided by the reactant concentrations. When K has a value much less than 1, the product concentrations are relatively small and the reactant concentrations are relatively large. K is equals to equilibrium constants. It tells how far a reaction goes before it stops changing. K shows the positions of equilibrium, whether product or reactants are favored. Next, Kc is equilibrium constant written using concentration mole per liter. And then Kp stands for partial pressure. R is gas constant, which is 0.08 to 1 liter per mole. T is temperature in Kelvin. And this one we call here is called the change in the number of mole of gas during a reaction. Moles that also mean moles of gases product, moles of gases reactant only. Gases are counted. Solid and liquids are ignored. So we really don't look at solids and liquid. For example, you can see there's N2 plus 3H2. This is reactant and the right side is the product. So we can see the moles at the product have 2, right? So we have to write 2. And then the reactants only have 1 mole for nitrogen and 3 for hydrogen. So we add them both and then we get to 4. We get the answer is 4. So as we know that this symbol is mole of gases product minus mole of gases reactant. So that's why we have 2 minus 4 equals to negative 2.
Now I will be explaining about Le Chatelier's principle. Le Chatelier's principle states that when a system at equilibrium is disturbed, the system will shift in a direction that reduces the effect of the disturbance and re-establishes equilibrium. There are 3 main factors that can disturb equilibrium. Number 1 is change in concentration, number 2 is change in pressure or volume, and number 3 is change in temperature. Effect of changes. If the concentration of a reactant or product is changed, the equilibrium will shift to oppose the change. Adding the reactants, equilibrium shift to the right, which is towards products. Adding products, equilibrium shift to the left, which is towards reactants. Removing reactants, shift to the left, and removing products, shift to the right. Effect of pressure. This only applies to reaction involving gases. Increasing pressure or decreasing volume, equilibrium shift to the side with fewer moles of gas. Decreasing pressure or increasing volume shifts to the side with more moles of gas. If pressure is increased, equilibrium shift to the right. Next, effect of temperature. Temperature changes affect equilibrium depending on whether the reaction is exothermic or endothermic. Exothermic reaction, heat is released. Increasing temperature, shift to the left. Endothermic reaction, heat is absorbed. Increasing temperature, shift to the right. Important. Temperature is the only factor that changes the equilibrium constant, K. Lastly, effect of catalyst. A catalyst does not change the position of equilibrium, does not change the value of K, only increases the rate of forward and reverse reactions equally. It helps the system reach equilibrium faster.
What are Kp, Kc, and Qc? They are used in chemical equilibrium to show how much reactant and product are present. Kc use concentrations, Kp use pressure, and Qc tells the direction of reaction. Kc equilibrium constant concentrations. What is Kc? Kc show the ratio of product to reactant, and equilibrium it use concentration mol dm minus 3. Meaning of Kc value: large Kc more product from it, and small Kc more reactant remain. Kp equilibrium constant pressure. What is Kp? Kp is used for gaseous reactions. It uses partial pressure instead of concentrations. And then Qc, reactant coefficient. Reaction coefficient. What is Qc? Qc has the same formula as Kc, but it uses current concentration, not equilibrium ones. It tells which direction the reaction will move. These example reactions.
We provide a simple notes for chemical equilibrium.